Hello everyone, this is Jiameng. Today I'm going to introduce our work about the DHSampling. It's the diversity-based Hyperedge sampling in gene learning with application to medical image classification. This work is part of my research project at the Baxter Lab under supervision of Professor Islem. To begin with, I will introduce some preliminaries for the graph. It may include the nodes and also it may include the node relations among different nodes. We call these relations can be the edge or links. It may links all the nodes into a large graph. The feature aggregation process in original or in the classic graph neural networks, it may in Hello everyone, this is Jiameng. Today I'm going to introduce our work about the DHSampling. It's the diversity-based Hyperedge sampling in gene learning with application to medical image classification. This work is part of my research project at the Baxter Lab under the supervision of Professor Islem. To begin with, I will give some preliminaries for the graph. It may include the nodes or the vertex. It may include the nodes embedding itself, and also it may include the links to link to nodes if they have some height of the relations. Hello everyone, here's Jiameng. Hello everyone, this is Jiameng. Today I'm going to introduce our work about the DHSampling. It's the diversity-based Hyperedge sampling in gene learning with application to medical image classification. This work is part of my research project at Baxter Lab under the supervision of Professor Islem. Hello everyone, this is Jiameng. Today I'm going to introduce our work about the DHSampling of the diversity-based Hyperedge sampling in gene learning with application to medical image classification. This work is part of my research project at Baxter Lab under the supervision of Professor Islem. To begin with, I will introduce some preliminaries. First, for the graphs, it may include the nodes or we call it the vertex of these self-embeddings. And also there are edges to link to different nodes to construct an entire graph. And the feature aggregation process in the conversion of the traditional graph neural networks that with the layers increase, the node embeddings update will need a lot of its neighbors layer by layer. It will cause the neighborhood exploration issues, especially for the GNNs on the large graph. So in the literature, there are also existing some methods to solve the neighborhood expansion issues, such as they have the sampling strategies, and it can be divided into the node-wise, layer-wise, and the subgraph-wise sampling based on the sampling subject. So, however, there are some limitations on current sampling strategy. First, for the node-wise and the layer-wise sampling, it still needs some special memory to store node and edge embeddings at each layer, and also their subgraph-wise sampling may introduce bias by treating samples as independent entities. So in this way, here comes the questions. How can we apply GNNs to large-scale data? And our solution is the diversity-based Hyperedge sampling gene learning. Here's the main framework of our proposed method. We want to combine the subgraph partitions and the subgraph sampling strategy together for the applications of GNNs on the large-scale graph. First, we use the subgraph partitions to reduce the memory computation of the large-scale graph. Also, we use the subgraph sampling to accelerate the GNNs learning. It's including 4 parts. We may introduce each of the parts in the following slides. The first is the Hyperedge construction. To solve the large-scale graphs in the memory demands, we use the Hyperedge constructions to convert all the graph into different subgraphs, and then train our genes on the subgraph to reduce the GPU memory's requirements. So, different to previous methods, we random partition each node to different subgraphs, and in this way we can solve the bias by previous method, and also we can have a continuous update of the graph among different subgraphs. And the second strategy is the diversity measurement. And since when we divide the entire graph to several subgraphs, this may significantly prolong the training time of the GNNs, since it needs to go through all the subgraphs. So in this way, we introduce a diversity measurement to measure the most diverse subgraphs among the partitioned subgraphs, and in this way, we calculate the topology, eigenvalues diversity, and also the embedding distributions diversity to measure the entire diversities. And in this way, based on the calculated diversity of each subgraphs, we calculate the most, or we select the most diverse Hyperedges for the subsequent graph neural networks training. In this way, we can not only reduce the GPU memories, and also we can accelerate the graph training. To train and evaluate our proposed method, we select the meta-minutes dataset, such as the organ-C and organ-S dataset, to train and evaluate our proposed method. And since this data is originally in the 2D space, so we first convert the dataset into a large-scale graphs based on the similarity of image intensities, such as for each images in the dataset, we consider this as a node. And also we calculate the similarities of image intensity to link to different images in the original dataset. And also, we find that there are some smaller intensity similarities. So in this way, we introduce a threshold to make the graph sparse. And also, after we construct the graph, here is the detail of the node edges and the feature vectors of node embeddings of each node. And we quantitatively compared our method with the most classic sampling strategy of the classic GNN. We find that on the organ-C and organ-S that we can find that our method not only outperforms in terms of the precision recall and F1, and also we can reduce the training time when we apply GNN onto different datasets. And also we conduct several population comparisons of each proposed component in DHSampling on the GNNs. We can find that with the random sampling, even it's training on the full subgraphs, our method, diversity-based sampling, also outperforms than the random sampling. And also we incorporate our method with graph-partition neural networks. We can obtain same conclusions as incorporate DHSampling with GNN. It demonstrates that our proposed DHSampling can be integrated to any classical graph neural networks as plug-in attributes. And in conclusion, our Hyperedge partitions achieve superior classification performance compared to random partitions, and also the diversity-based sampling strategy can accelerate the training time while keeping comparable classification performance. Okay, that's all for your listening. If you have any questions, please feel free to contact me through emails. Thank you.